night while sleeping that many of my slides are the same topic. However, they look slightly different. And it is said that if you know a place, you feel comfortable. It's the same way when you know a figure and you know how it looks like, you feel more comfortable and you understand better. So just to be sure that you understand, so I'll give you a review first today, and then we'll go to more important things later about the whole picture. So, but this review shows some additional pictures that I've not shown, which I normally show in my lab. There was a man named Engelmann. He actually was German, but he lived in the Netherlands. And he did one of the most fascinating experiments. He put an alga called Spirogara, whatever, depending on the pronunciation, and he put aerotactic bacteria and put different wavelengths of light. And he found that the bacteria accumulated in the blue and in the red. This was the first action spectrum of anything ever done. So beautiful. Like a picture. Use this. Yeah. All right, so these are some of the 4 basic pictures in the seismic diagram. What are they? Some of it I assume that you know it, so I didn't use it. So, the light has 2 components parallel to the electric component and magnetic component. Then we discussed this, the wavelength of light. 400 nanometer is blue, 700 is now, there is a red drop, and as you saw, you plants use the blue light and the red light, and you see how the different energy of the other radiation, gamma rays, X-rays, where this, by the way, is only this part, X-rays, very high energy, ultraviolet, higher than the blue, and the X-rays where Umena of Chen made the discovery of the structure of photosystem 2 was said that he had destroyed it because it's very high energy, it does destroy it. And then it's infrared, low energy, microwave, we don't use it, or radio wave. So basically, that's just to give you the wavelength in nanometer. Now, all right, so what is this? How you measure the absorption of the pigment? Let's say I say it absorbs blue and red, so you give different wavelengths of light. Here there's a prism or a grating, monochromator, a grating example, and there's a photodetector, and you vary the wavelength of the light of this, and you measure how much the light is absorbed. If less light comes through, it's more absorbed, and you have the absorption spectrum. That's how you measure the basic absorption spectrum. And then I showed you a slide from my title of my book, or the cover of my book, it's a solar radiation, and then you have this is the absorption filter, and that's the energy that's reaching the earth because CO2 and water absorb. So this is basically another way of showing the graph that I showed you, but more for a textbook type. My graph is more interesting. Now we talked about absorption. An electron, the 2 spinning electrons, opposite spin, it goes to, when you have more energy, E equals to C lambda, blue light, it's from the higher energy, and you have less energy, but see, these are quantized energy levels, so you have a question here or here, and from here, you can lose energy at fluorescence, which you will see next time, we'll talk about fluorescence, and then the absorption spectrum is directly related to the energy level diagram. All right. So when it's more absorption, it's related to this energy. So it's plotted another. wavelength scale and yet and energy. Now, as I showed you in one of my figures, that they are absorption by many pigments, and you have in the cyanobacteria a blue pigment, phycoerythrin, and red algae, phycocyanin, here, and then chlorophyll, and then this is in another chlorophyll, bacterial chlorophyll, and so on. Carotenoid, yellow pigment. So that's the absorption spectrum of it. This is the structure I showed you before in my talk, but this is in the book. So you have the single bond, double bond, electrons are running around the system. That's what the last one is being used. And there's the tail, or phytophage, which I didn't talk about because we didn't do the function, it's just the anchor. So it's in there. And then these are the carotenoids. And this is the Nobel Prize winners. I already showed you the picture. The bile pigments, the bilin, which are the phycocyanin. Now this is the absorption spectrum, and this is the spectrum of photosynthesis. And it is basically here very different, where the red drop comes from this. Now, I talked about the photosynthetic unit, and your book has a picture. As this picture of these antenna, I said 400 molecules per oxygen, actually 300 molecules per reaction center, and then energy per top, and we have discussed the energy. So these are temperature independent reactions, and the first reaction is also independent because the donor and the receptor sit very near each other, and you have energy. Here is the experiment of Emerson and Arnold, which they have in the book. Is that difficult? So we're just reviewing the size and Geiger picture. So the oxygen produced versus flash energy, and this increases with time, and the initial flow of the reaction is what is the quantum requirement. So 9 to 10 photons per oxygen. We talked about Emerson's work and his professor Warburg and the controversy between the two. And Emerson was right, and we approved Emerson right later by following. So this picture is on your. Then I explained the Emerson enhancement effect. They have 2 units for one light and then 20 for another, and together 30. So this is explained in your book, the Tides and Tides book, which all of you must read chapter 7, and those who are not here and they are friends, please tell them. Of course, there will be a final exam, and so the party will give it, and all those things will definitely be in. Okay? So they should read it now because there are more reading when we come to lecture. So this is the absorption spectrum. And this is the quantum. This is badly done diagram in the book. I am much more direct. I showed you direct data from Emerson and Lewis paper. It's just done by hand, and it only shows that the quantum will drop. Of course, it should not drop because you already taken care of the low absorption, and it should have drop. Now, how he explained the Emerson effect in this manner. He said, far is light on, and you have certain amount of photosynthesis. Then they put the red light on the same value to give the same number of oxygen. So just change the light intensity. So it's a 2 plus 2, and you expect 4, now you have 10. So both lights are on. This is the Emerson. And as explained in your book, Tides and Tides, I explained it somewhat different. And this is again the Z-scale, which we're going to talk about today, but many people are not here. So this is again the photosystem 2 and photosystem 1. And we gave the actual detailed experiments of Huygens. He was proving that one light oxidizes the cytochrome, the other light reduces it. That's why it's resistant. This scheme in your book includes the kind of photosynthetic unit, and it tells you what the final product is, NADPH, and it tells you what the final product is, oxygen, and both light product and red light are used. Here is where I showed you several pictures of the chloroplast. I showed you other pictures of chloroplast, and here like stacks of granum, like coins, put on one top of the other. Rupiah. Rupiah रखे हैं And then this is the Ghana, and this is the whole within the Newman, and so on. So these pictures basically are the same pictures, but drawn differently, and maybe some are simpler than that. So here is, I already showed you this. Somebody actually asked a question about where solar system 2 is. And here you see there are this says 80% for here. The solar system 1 is here. There are some solar system 2 out there. I don't know who asked the question. But mostly most of the solar systems are here. And you have the cytochrome, which is here as well as here, cytochrome, solar system 2 is mostly here. And light harvesting 2 mostly here. So this is only in a thylakoid membrane, which are fast, but when cyanobacteria and other cases, this is not so. This is not necessary for photosynthesis. It's just an evolution. So have fun. Okay, the other point which we shall discuss next time is the light energy absorbed by chlorophyll B. I've already mentioned 100% of it is chlorophyll A. We'll see in tomorrow why we know that. And so the energy goes from carotenoids to chlorophyll B to chlorophyll A, which is taken. It's a downward energy process. And now this is exactly how some of the things look like. Not exactly, but they kind of in the picture. You have chlorophyll B and chlorophyll A. Both are in the light harvesting complex. They're close to each other. And they will transfer energy, B will transfer energy to A, but A will not transfer energy to B. Why? Because you have energy level. So B is lower. Sorry, A is lower than B. B is high energy, so down the energy transfer. So not that it is impossible. We can make it happen. And people are able to make it happen. That is called uphill energy. And that actually happens in one bacteria, in which it always does the uphill energy transfer. We are not talking about that. So this is another picture of the Z scheme, which was the topic for today. And again, it shows the same thing, except now this scheme has all the components that my scheme has here. The scheme has the same components I have here, except they don't have the bicarbonate. And this is the same components that I showed you the other day. I think you see complex 1 and execution phase. But my real scheme, which I will not do it today or bring it tomorrow, has its time. Now, this is a more important concept that we didn't talk about. So why we need energy to go? So you have to remember one simple equation: delta G, which is free energy. But you can remember delta G is the free energy equals N, the number of electrons, and delta U. F, which is a Faraday constant, from delta U. So basically, when you have a molecule like E680, which has a redox potential, we call positive redox potential. That's just arbitrary decision by somebody, which one we call positive, which one we call negative. So it was a poor reducing agent. It's a donor, an acceptor orbital, let's say, and it's a ground state chlorophyll, 2 electrons moving in the opposite direction. But when the light comes, 1 electron jumps up, and you have electron higher up, molecule excited, so it becomes a good reducing agent. You can reduce something which has that potential, which is more negative potential than it. So this is a very crux of the reason why energy is needed to go from lower energy to higher. Okay? Don't need to know this, except to show it's a very beautiful system, and you have molecules there. That's nice. There's lots of pictures in your book, and it shows exactly where the proteins are, the millions of proteins. Now, this is what I'm going to talk about from carry on to the last lecture. But I will do that in a minute after I show you So these are, by the way, because I'm being recorded, they must know that this is coming from Tide and Zyder. I did not draw. That's why we're always afraid of forgetting to say something and being recorded. Right? So this is the plastoquinone, which is between the two photo systems. This is how it looks like. And when you get one electron, it becomes a plasticonium, like QA and QB here, we'll discuss, it becomes QB minus, it's just bound, and then when one more electron comes and two protons come, it becomes plasticonium. And these are cytochromes, which I'll come back when we talk about cytochromes. And this is, I'm just showing you all the slides in your book. So you read them ahead of time will be better, and you will understand what I will talk about later about the cytochrome F complex, how it behaves, how does it, what we call the Q cycle, how does it make more ATP, and so on. So this is a picture of the book with photo system 1 here, and that shows that 2,700 electrons go from here to here in the different area. And this structure is also known to very high resolution. It was done earlier in Berlin, but finally in Israel, but not enough. Okay, so now where do the herbicides work? Where do they kill? Why do they kill plants? What did they do? So we picked up two. Your book had picked up two of them. One is diuron, DCNU, and one is paraquat, metal diuron. So the way DCME works is DCME actually essentially blocks electron flow between the electron carrier quinone plus the quinone A, and it's both plus the quinone 9, but we call it QA, it's bound tightly and not. The DCME works not by killing it, but actually by physically removing the QB from the site and throwing it out of the system, and therefore it blocks. All the diagrams have errors because they want to convey to you the basic idea is hard to convey in a diagram. So basically, you have to know that it works because it goes and sits exactly where QB is sitting, removes it, and therefore it comes. Here, paraquat metal diarism works because what it does is not blocking it here, it actually drains electrons onto itself. And therefore, it kills the plant because it will not allow CO2 to fit. So that's how these two work. And we have seen this picture already. This is the experiment of Andrei Agazov, how you put the chloroplast at the pH. This is a nicer picture than what I showed you. And then he put it and then put in pH 8 and put 8 in pH. Down the world, proving that delta pH can make it. It's a beautiful experiment. Mitchell got the Nobel, but this is for the somebody is writing something on bacteria, which is fine, but I will not go through this. But we will talk about how plants protect themselves, and all these pictures of the chemicals involved, validantin and antivantin are there. Basically, I just showed you the slides of chapter 7 in your book. I'm encouraging you to read that chapter, so it will be easier for you to follow up on it. Now, yeah, please. Yeah, go ahead.
Sir,
I was just telling him to put the other. Yeah.
That P680 is a weak reductant and P700 is a strong reductant.
No. Medium. Strong is a bad word.
But in the slide I saw that.
No, here is the slide. Here is P680. Here is P700.
Yeah.
It's medium. It's not strong. The strong reduction will be here.
Yeah, there only. Excited state.
So basically, this is when it is oxidized and when it's excited, it is a strong reduction. So everything becomes strong because of the light raised electron on a higher energy level.
No,
so P680 itself, without being excitation, is unable to reduce anything. But when the electron is raised with the light, it is here. P680 star, and all redox potential are with the couple. P680 plus. P680 star, P680 plus, or P6.
Sir, if we compare both P680 and P700 when they are in their excited state, so is there any significance that P700 is more power to reduce as compared to the P680?
Yes.
Is there any significance in relation
Of
to
course,
what?
you got things which require more energy,
Okay.
and therefore P680 will not be able to reduce any of these entities.
Okay.
Therefore, you need to like that. And there's always a story, because I know all the stories. I've been through the history. Daniel Arnold and Berkeley, who discovered photophosphorescence, claimed 3 papers in PNAS claim that P680 star reduces energy.
Yeah. Okay.
Because if you look at the energy, P680 star has enough energy to reduce it. Why doesn't it do it? It's the question.
Yeah.
It's because thermodynamics works in a way that there's always a loss of energy before something can do. So it is efficient to reduce pheophytin, but not as efficient to reduce let's say what. And they I don't know whether there was a fake, they faked it, or some scientists made an error or what, we don't know. But that's what they claimed, and they were wrong. And Arnold kept the entire scheme is wrong till his death. There's only one light reaction. Okay? And then, because energetic-wise, it was okay. Then he later, when one of his students who I talked to, Max Twain, said, no, there is a Emerson effect. So he said, oh, this is a Emerson effect because it's the same for the system 2, for the system 2A and for the system 2B. So the brilliant people have a way of putting themselves in the end. Is that okay?
Yeah.
Can you show? So basically, since the class is not so popular nowadays, sorry for that, but they have to read it themselves or talk to me. So we talked about many. So we'll do the discrimination because I think I can better to have everybody together. I have written a review with Madi Najapur, Ateti Maladam, Sulman Al-Ahmadi. I published in Biochemical Mathematics the Actor, and you might wonder how I gather such a group. Well, I really didn't gather. Suleiman is in Moscow. I've known him for many years, and he's worked on Baikal. That's where I've known him. And the Suleiman knew Madi Najapur from Iran, and then his student, Madi's student, Ateti Maladam, she came to a conference in Azerbaijan, in Baku. So we somehow, without meeting my first author, Madi, which I still don't know, I've never met him, we wrote a review called Biological Water. This review will be on your place, Google Drive. I think it's already there. Please check it. It's a good review. It talks about this review. This particular review is being used in University of Alabama with Professor Ort for teaching biological adaptation. So when John uses it, I feel okay. Deep brain thing. All right. So let us see. So this is not the only review, and one of the biggest problem of being taped is that you cannot forget the names of the people, and there are many people who contributed to this field of optics. It's the most exciting thing in the world because it's the only system which can make oxidized water flow. And water is the most abundant thing, and therefore all the artificial people are eyeing to understand the details. And we all hope that somebody gets a Nobel Prize, but there's so many people that I think it's not. So this is a picture. I don't know where it's taken, but I always thank people when I got the picture. This is art. Shows this oxygen. I mean, you saw the picture of Ingenwoods, and I have my own picture, which I published in my science. But this is a much beautiful picture. So just to get a feeling of oxygenation of the atmosphere by water oxidation. This is a slide taken from review by Martin Meyer. That most people, most women take their husband's last name. Right? Last name, and I have several other friends who are doing that. So equality is the key. So what this shows is when these things evolve. The earliest rock, this is giga-years ago. Here. The earliest autotrophic life, then came the cyanobacteria, and the purple bacteria is kind of hazy things here, one doesn't know. The green sulfur bacteria, I think somebody in the class wanted to write about bacteria, which is good. And then the photosynthetic eukaryotes, land-based. And look at the iron deposit, right? And look at the oxygen concentration. The oxygen concentration, and one is the signature molecule evidence, this one, and then one is the fossil evidence, the color segment. That's clear, but it is clear that it is increasing, and it all comes from the fact that we have photosynthesis oxygen. Yep. Very good question. It's a very difficult question. You send me today. Now you'll look for me. Very good. I'm very glad that you did it. I did too. And I asked the same question, but I don't have yet the answer. Don't remember exactly. Until the answer is there, it's just going to come. You do send me. So basically, 3 billion years of evolution, and the far-ranging biogeochemical have produced only a single group for catalyzing water. Single grouping. So the evolution of a single enzymatic solution, despite access to every ecological unit, the vast quantity of seeds is so unique, so important. I think this is one of my papers. I don't know, maybe it's from the review. All right, so we talked about this concept earlier about free energy. Free energy delta G is N F delta E. E is redox potential and is number of electrons at the acceleration. Going from positive to less positive delta E is what? Y is light energy, electron, light water, and you look at the redox potential. So let's look at the hydrogen. Hydrogen is given minus 0.4. That should be in another unit is 0. This unit is being used today, minus 0.4. And look at the water, plus. So you have to have another entity which should be able to oxidize water, and that is P68. It's a chlorophyll. All chlorophyll that is. I have a review published that I should give you called Why Chlorophyll A. And same chlorophyll in photosystem 2 at the P680 place at plus 0. Some electron volt of redox potential. Same chlorophyll in P700. You have that question. Same chlorophyll, 2 molecules plus 0.4 electron volt potential. The same chlorophyll at A0 is minus 0.4 electron volt. So the same chlorophyll molecule, depending upon the environment where they are, different properties. So the water is there, so we have to have P680 involved, which is the correct redox potential. Then look at NADP minus 0.3. So you have to go from plus 0.8 to minus 0.3. Almost 1 electron volt. You should be able to do it with 1 electron like that. Because like at 1.8 electron volts in red light, but we don't, because of dynamics in which we use energy to do things, and nature has evolved so things. Anyway, and ubiquinone, alcohol is in the middle, plastic 1.1, and this guy and such that. Anyway, we don't need to know all the other ones. So the basic reaction, as you see, is 4 electron topic, 2 oxygen, the other day we see all 4 four balloons, and that's the picture shows where everything is. Manganese, boron, oxygen, calcium, and then you have bicarbonate there and you stuff that. And this is how the structure looks like. So you have first, and I showed you two processes the other day from Gandhara's group that, but I'm showing only one. The P680 is transfer the electron to purification. It has no magnesium in the middle. That's the only difference of purification with chlorophyll. And then it goes to the quinone plus the quinone 2A, which is down non-iron to another plus the quinone 2B and bicarbonate. And tyrosine is delivered to electron. One is tyrosine. There's the manganese one. The tyrosine that actually delivers to electron 2 pieces of it. So 1, 2, 3, 4, 5. So it jumps. The reaction doesn't go in one way. Why? When you ask the question why, very complicated. I don't know. Because it has to do with the chemistry, it has to do with the positioning, energy levels, and so on. Multiple factors. Water molecules? No, I told you there are 4 water molecules. We don't know which 2, but now we know that there are actually 6 water molecules. And 2 of them are slightly far away. And which of the 2? The 2 bound to the calcium, 2 bound to the calcium, and 2 bound to one of the manganese. And most theory is that it is perhaps one group thinks it is this oxygen because they are doing side-directed mutagenesis, and another group thinks it is this. So it's not yet solved where the real water molecule is. And that's the tyrosine. So now this is the real manganese clock. This is really where things happen. And what happened? We talked about X-ray. By the way, this picture has many origins. I said for the tape, you have to be sure. There are many friends involved. Vitalia Chandala's group, Kentawa's group at Berkeley, very heavily involved. Then Holger Dow in Germany, and I may forget. Those who are listening, please know that I'm being very careful to say there are many people. So now let us look at the states. So we said in the darkness, that's the clock. I said to explain very well that S1 is stable. So when you start planting the dark. So now, do we know there are 4 manganese? Do we know the oxygen? Most experimentalists have come to the conclusion based on synchrotron results, which are not too easy to explain, that they can tell where manganese is. So majority of the people have come to this conclusion that there are 2 manganese in Mn4 and 2 manganese. So one flash of light comes in to P680 plus, and then this has given off is an electron to P680 plus, then S1 goes to S2,